Hello, my name is Katie Perkins, and this is my presentation for Lab 3, Magnetic Field of a Permanent Dipole. The purpose of this experiment was to measure the distance dependence of a magnetic field due to a small bar magnet and compare this measurement to the distance dependence predicted by the equations for on- and off-axis magnetic fields. My goals were to find the N and K values using the generated plots, solve for the magnetic dipole, and compare the predicted and observed 45-degree measurements for magnetic field. My results were that K was equal to 6.98 times 10 to the negative 7th, N was equal to negative 2.94, the magnetic dipole was equal to 3.48. The model predicted that my 45-degree magnetic field would be 2.62 times 10 to the negative 5th teslas, and the experiment showed that it was equal to 4.86 times 10 to the negative 5th teslas. The relevant equations were as followed: the off-axis magnetic field equation, the on-axis magnetic field equation, the distance dependent of a magnetic field, and the linearization of this equation. The experimental model had three parts. One was the setup, two was the distance dependence of the magnetic field, and three was measuring an off-axis magnetic field. The first part of this experiment was to compensate for magnetic north. I did this by going far away from electronics, metals, and other magnets and putting my phone on a flat surface. Then I slowly rotated the phone until the X component read 0. In Atlanta, the net magnetic field should be about 49 microteslas, so I confirmed this value. After doing this, I set up my meter sticks to point in the east-west direction. Then I placed the bar magnet to the left of that meter stick along the east-west direction. I slid the phone up and down until the X component was at a maximum. I marked this spot with tape. Then I flipped the phone 90 degrees and did the same thing in the other direction. I marked this spot with tape as well. The intersection of the two pieces of tape should correspond to where the sensor is in the phone. The second component of this experiment was to measure the distance dependence of a magnetic field. I moved the bar magnet along the east-west meter stick until I found the spot where the X component of the magnetic field read 20 microteslas. I repeated this 2 more times. I repeated this whole procedure for values equal to 70, 120, 170, and 220, and I input these into the Excel document. The third part was to measure the off-axis magnetic field. I did this by finding the spot where the net magnetic field was equal to 100 microteslas. I assigned this distance to dperp. Then I took that same distance along the east-west direction, and I moved my phone up the same distance in the north-south direction. Then I recorded the X, Y, and Z components of the magnetic field in that spot and put it into the Excel document. My observations throughout this procedure was that when the magnet was very far away from the magnetometer, the sensor read close to 0, and then as it moved closer and closer to the magnet, it increased in magnitude. My sources of error were that I kept accidentally bumping into the phone sometimes, so I'd have to reset it. In addition, it was hard to get away from steel and iron objects. There was possibly an inaccurate determination of the magnet sensor, as I noticed that when I was on equal distances away from the sensor, I got slightly different results based on what side I was on. In addition, my ruler had a little metal strip on it, which was causing some problems. I linearized the distance-dependent equation and got the following values. My K was equal to 6.98 times 10 to the negative 7th, and my N was equal to 2.94, negative 2.94. Then I set the magnetic field on the axis equal to this distance-dependent equation and solved for my magnetic dipole. This was equal to 3.48. The first part of my code, I set up all of my constants and then wrote a function to find magnetic field. Then I modeled 2 on-axis observation locations and 4 perpendicular locations and made arrows for each of those. Finally, I calculated the 45-degree angle off-axis magnetic field at that spot and printed my results. In the model, the small white thing in the middle represented the magnetic dipole. As you can see, the 2 orange arrows show the on-axis magnetic fields, while the 4 blue arrows around showed the perpendicular ones. The pink arrow on the side shows the 45-degree angle. From my model, I calculated that the 45-degree angle magnetic field should be equal to 2.62 times 10 to the negative 5th teslas, while my experiment showed that it was 4.86 times 10 to the negative 5th. These were of the same order of magnitude and fairly close. If I did not calibrate my phone to point towards magnetic north originally, all of the x components of my measured magnetic fields would have been off by a set factor, as long as my entire system was off by that same amount. And if I were to put two identical magnets back to back and do the same experiment, I would have gotten the same pattern all around. The magnetic dipole would likely just be stronger. Thank you for listening.